Well, welcome everybody to our science seminar this week. Glad to see you here this Thursday. Today we have a really interesting talk about fluid dynamics and all those things, forces that you take as engineers, physicists. So this should be really interesting. We have Dr. Pack from Baylor University. He's part of the School of Engineering and Computer Science. Dr. Pack has his bachelor's degree in engineering science from Pennsylvania State University, where he grew up there in Philadelphia. He's got a master's in sustainable engineering, so that way he can keep his job as an engineer. Sustainable, right? And a PhD in mechanical engineering from Drexel University. He also did a postdoc at Princeton, and from there he has gone to Baylor, where he is, what are you, an assistant professor? Yeah. And he's looking for students to fill his lab, right? To do all kinds of exciting research with him. So if you're thinking about, what is going to be your career in engineering, you want to go to grad school afterwards, here is a good opportunity to join a sister school. Baylor is not so far away from us, just a couple hours down the road, and you could come back and visit all your fraternal friends, on the breaks. Yes, and it'd be a fine place to be. So let's welcome Dr. Pack.
Good morning. Thank you so much for allowing me to be here. I'm really honored to be able to speak in front of you to share a little bit about what we've been doing in our research. But before I do that, I'd like to just take a brief survey of who I'm speaking with. So are there any freshmen in the room? Oh, wow. Okay. Sophomores, juniors, and seniors. Awesome. Okay, wow. Okay, it's really nice to speak to folks who are maybe just getting started. And so some of the verbiage I use might fly over your head, but don't worry so much. I won't be offended if you fall asleep. It's not a big deal. But I hope I can try to motivate you to try to understand why we study some of the mathematics and physics that you do study in your classroom, and how that could relate to real-world problems that some of it might seem very specialized, but they do have a broader application, okay? And so I need to take another survey. How many of you guys had a fried egg this morning? Okay. What about pancakes? Nobody had pancakes this morning? Did anybody have breakfast, or are you guys all engineers, so you don't? Okay, so what about coffee? Anybody like to drink coffee in here? A handful? Awesome. So what I'd like to try to motivate you today with is this idea of interfacial science. And the idea is that we live and breathe within a fluid, mainly air. We interact with water as well. You can't live without it. But what's surprising for maybe some of you here would be that there's this other field of science that's somewhat multidisciplinary, and it's called interfacial science. And a lot of cool things happen at the interface, like when you brush your teeth or when you drive your car to get here. Surfactants in toothpaste, for instance, help clean your teeth. And we have to atomize fuel to be able to allow combustion to happen and get your car generating thrust, right? So being able to do anything just from the moment we wake up till when we go to bed, stuff has to be happening at the level of the interface. And when I say the interface, I mean any time you have air and liquid, or liquid and solid, anytime the phases that you learned since high school, like let's say liquid, solid, and gas, whenever they're interacting with each other, that's what I mean by the interface, okay? And a lot of cool things happen. For instance, how many of you guys have heard of the Maillard reaction? Okay, awesome. So I'm not a chemist, so I don't claim to be an expert in this, but I'm sure there are experts here. But pancakes wouldn't be the same without that at the interface, at the level of where this extra high heat is doing some cool things with chemistry to give you these really cool flavors, okay? That's about all I can say about the Maillard reaction, okay? But so besides the everyday applications, and hopefully I'm convincing you that science at the interface is interesting and it's relevant to everyday life, but it doesn't take long before, and I'm not endorsing any of these news outlets, but these are just random articles I found in the last couple of weeks that really reminds me how important it is to study things at the interface. Okay, consider the CPAP machine. Anybody know what a CPAP machine does? Can somebody explain? Anyone? Yeah.
The CPAP machine applies pressure to your airway to keep it open.
Awesome.
So you can sleep.
Right. Yep. So I don't know if you guys have heard of the recall recently, but there's a toxic polyurethane foam that's been kind of breaking off, and it's not good for patients, and so they have to fix this issue, and it's all happening down at the level of the interface. Okay. Not just health. There's many, many, many applications in health, but even in the music world. Stradivari's violins, which are very famous violins, which I don't know much about either, but there apparently is a very nice coating on this violin that we still don't know what it is, but it's helping produce these amazing violins. But again, it's a liquid film over wood, and therefore, again, it's an interfacial science question. And lastly, we live in the state of Texas, and so agriculture is a very big thing here, right? And one of the issues, prevailing issues in agriculture, is this idea of chemical spray drift. What do you think that might be referring to?
Crop dusting.
Yeah.
Crop dusting.
Okay. And what does that do?
Applying pesticides
Yeah.
to fields and things.
Yeah. So if I sprayed herbicide on one side of my farm and there was enough wind to carry that into, say, trees in another farm, they could damage trees in another farm, or worse, it could injure people, right? But that's all happening at the level of the single droplet. And what you might be surprised to find is, now I'm going to camp out on this idea of pesticides throughout this talk, or droplets really. But at least for the next minute, I'd like to talk to you about sprays in general, especially in the context of agriculture. More than 90% of sprayed pesticides end up as runoff, meaning it doesn't hit the intended target. And so as an engineer, it makes you think, why is that? There's obviously many reasons for it, but I'd like for us to think about, well, how do we start to even think about this complex problem and try to parse together the basic fundamental physics that makes up what is happening. At least try to understand the business as usual case and try to improve upon the various processes, okay? And so that's what I'll start to talk about next. But as an aside, so there's a lot of freshmen and sophomores in this room. I think when I was in your shoes, I got very involved with the humanitarian engineering program at Penn State, and I told God, if you get me into becoming a faculty, I'll go wherever you want, say the Middle East, but I ended up in Central Texas so far. So it's, as I'm speaking, I'm always thinking about how does this also influence downstream, not only our own country, but also places that have less resources than us, or they're marginalized in society. I'm always thinking about these things. Okay. So coming back to this, I want to zoom into a single plant for a second and say, let's look at, okay, so if we can't try to, if we need to break down this problem, let's try to look at a single plant for a second, and let's look at the distribution, the size distribution of drops from a single spray. And it typically is submillimetric. It's on average, it's a couple hundred micrometers. 100 microns is about the thickness or the diameter of your hair, so these droplets are already pretty small, okay? And further, you could look at a single droplet level and see what's happening. But when you start to think about how a single droplet interacts with different surfaces, you have to start considering this idea called wettability, okay? And the idea is that if something is very wetting, then the angle that the droplet makes with the substrate is less than 90 degrees. And if it's non-wetting, it'll be greater than 90. And whenever you hear about materials that are hydrophobic or super hydrophobic, that means that contact angle went above 150 degrees. Okay, so and it's very easy to let them be not as sticky. Okay, and some leaves also are just very naturally hydrophobic as well. So the lotus leaf effect, for instance, is a phenomenon that people have been trying to replicate for quite some time, where droplets are completely non-wetting. But the problem with super hydrophobic technologies is that it's not very robust. So it's something that there's still a lot of ongoing research in. Okay. So for wetting droplets, even on glass is very smooth, but even glass has very minute, what we call asperities or minute roughness, and can form what's called capillary bridges right before contact and start the wetting onset. For super hydrophobic surfaces, they can be created with nanostructures. So basically, it's infused with air. Since water and air are not going to mix, if you infuse the surface with air, you can prevent the water from wetting the surface. Okay, so let's see if this wants to go. Might be frozen. Sorry, I think it wants to restart.
Oh, shucks. Okay. Any announcements during the break? It's a great course being offered in the spring called Patent Law. Holly
Who
Size,
teaches this
3223. A very, very credible teacher there. Yeah. So if you're interested in how your degree is going to, there's back.
So say we're looking at a single droplet now, and you want to make these droplets stick better because some plants are hydrophobic. The leaves can be. Scientists have seen even over 20 years ago that if you add just a very small amount of polymer, say polyethylene oxide, it's a large molecular weight polymer, about 4 megadaltons, and at least in this study. And this video is from another publication 19 years later. They're just showing you the dynamics of how polymers allow droplets to stick. Okay. With even as little as 100 parts per million, or about 0.01%. So these are maybe, if you look at how we formulate these solutions, it's a very, very tiny amount of polymer that allows these very interesting dynamics to happen, okay? But in a spray, you would think that because there's many droplets, that it should form a film. And so how do droplets then interact with a film, right? Would be a question that I would leave you, because you can kind of see visually not all the droplets are sticking to the surface. So one of the things that we started doing is, okay, well, why don't we look at how a single drop interacts with film then? And what we found is that under certain conditions, the droplets will impact this film. So this film right now, so whenever I talk about a film, it's either going to be a very viscous oil film or just a water film. I'll let you know when I'm using which. In this case, this is a water film, bless you, for about 10 microns in thickness, and the droplet's about 2 millimeters in size. And a question that we had was that if you have a water drop impacting a water film and it bounces right off, did that ever make contact? But it sure looks like it's making contact, right? And so this singular question during my PhD actually made me go on an endless rabbit trail for why this happens. And that's really the mission of our lab is to glory in God's creation and understand that the things that you discover help you to understand really complex phenomenon. And the more you dig and dig and dig, the more you appreciate God's creation, right? And so I don't know if you guys have heard of Psalm 111:2. It's also called the Researcher's Psalm in some contexts. Greater are the works of the Lord, studied by all those who delight in them, right? And so why do I do all this stuff? It helps me to delight in God's creation. When you think about, and so today I was going to talk to you about both drop impact and evaporation, but because there's just so much, I can only talk to you about drop impact. And so when I say life cycle, it's about 10 milliseconds instead of it being like over the course of minutes, which would happen if I was waiting for the droplet to impact and evaporate completely, okay? So, and these are, this is my website. This is our students. I have 4 graduate students and 2 undergraduate students right now who are working on different problems. And really without them, I would not have a lab. So I'm really grateful for that. And if you're interested in seeing my website, you can check that barcode, which was invented in Drexel University and where I came from. And I can't go very far without acknowledging a lot of people. This is not a comprehensive list, but I had the privilege of working with a lot of amazing people, walking through the halls of Princeton, wondering how I got there. But God does amazing things, whether we like it or not, right? And so, and most recently, we had the privilege of obtaining some NSF funding to do some of this work, and so we're really excited to have more people join us with our work. Our work is not limited to drop impact. We do a lot of work in microfluidics, but also drop impact, colloid transport, and complex fluids. I'm sorry, I probably should have checked this before I brought it onto this computer, but these topics might seem unrelated, but there are ways in which that they are connected. I connect complex fluids with microfluidics when I think about mixing and separation problems. And if instead of having wall-bounded flows, if I need free surface flows, I study drop impact. And if we want to see how the droplet will then evaporate after impact, and if evaporation is important, then we start considering colloid transport. And whenever you have, colloids are particles that are very, very, very small, typically micrometers or smaller. And when you have a lot of them, you have to start considering the forces that are relevant to when you have many, many particles, and you may have to even consider the field of rheology, which is another sub-field that we dwell in. Okay, so I'm going to skip this because it's hard to see, but I want to talk especially about drop impact today, okay? Okay, so let me show you a little bit more introductory slides on drop impact. Drop impact, I said, was important for coating, agriculture. It's also important in spray cooling, combustion, even in inkjet printing, let's say flexible electronic displays. You want to be able to print and repellent surfaces. And what do I mean by repellent surfaces? So let me try to show you a couple of slides on what I mean by that. About 10 years ago or so, there was a group in Europe who came up with this idea of infusing a liquid into a hydrophobic surface to form a omniphobic surface. What that means is not only is it water repellent, but it can be repellent to anything but itself. So even oils. So here you're looking at a video that was created by this Slips Technologies. On the far on your left is a Teflon, in the middle is a super hydrophobic surface, and then on the right is this liquid infused surface, or SLIPS. And you can see how the super hydrophobic surface does really well until you hit it with silicone oil, which is a very low surface tension viscous liquid. You can see how it's hydrophobic, but it's not oleophobic. All right? But the SLIPS is both. Okay? And the way SLIPS works is that there's a very thin film of, let's say, a fluorinated liquid, and it can repel even oil, but which is all nice, but what we don't know in the literature, what we didn't know at the time, was how do droplets interact with these films, and what are the most basic governing physics? And so that's the question that I had during my PhD, okay? And this surface was motivated by the pitcher plant. So when the pitcher plant leaf is very dry, ants can walk all over it, but it can actually excrete a nectar that forms a thin film, and then the ants will hydroplane into the belly of the plant to be digested. Okay, and so this was a bio-inspired technology that has a lot of applications. It has anti-icing, anti-reflective, anti-fouling, anti-adhesive, on and on and on. And it has a lot of unique properties, like for it being omniphobic, pressure stable, can even be optically transparent and self-healing. Okay. So you take a porous solid, you infuse it with a fluorinated lubricating liquid, usually, and then you have this sort of super thin film that will prevent droplets from sticking. Okay? So the question that I would have is, well, how to drop, and oftentimes it's some sort of oil, so we need to know how does a water drop, for instance, interact with an oil film. That's why in the beginning I said I'll either be talking to you about water drop on water film or water drop on oil films, okay? Okay, so I come back to this video, and I said when we first saw this, we were just so mesmerized by it. We thought, well, why does this happen, right? Is a droplet actually making contact or not? And how can we image it? And it turns out that two liquid surfaces that are trying to interact, they don't necessarily have to contact. You could have two droplets that are impacting each other, let's say in a fuel spray. And if you guys ever pursue graduate school or research, even now, what you quickly find is that you go on what's called a literature survey. Maybe you've already done that in some of your coursework, and you end up following a rabbit trail, and you look for the first person who ever did this. And it turns out Lord Rayleigh already looked at two droplets that never quite coalesce, almost probably 150 years ago. Okay, and so it's always sad when you realize, oh, somebody else thought about this decades ago, but it's also humbling and motivating at the same time, right? And so Lord Rayleigh may have thought of or have observed this before, but he didn't have high-speed cameras and fancy optical techniques, and so that's what I'm going to show you next is, well, how do you image below the drop? Oops. And so we did two things. One is we used the principles of interference, light interference, and total internal reflection. How many of you guys have taken physics where you learned about total internal reflection? Maybe, some of you. Don't worry about it then. And another concept is this idea of interference. And the ideas are that the black and white rings that you see on the right translates to very small changes in the thickness of the air gap between the liquid film and the drop. And so these are bottom views. We're looking from the bottom. I'm going to play it one more time. Took my advisor 2 years to understand what I was doing here, so it's okay if you don't understand what you're looking at, okay? So on the left side, if on both sides, if they turn black, that means contact was initiated, okay? If it's a darker gray, that means there's a film of air that's hundreds of nanometers thin, but the droplet itself is millimeters wide. So that aspect ratio is huge, okay? Several orders of magnitude difference. So all you have to understand is that on the right, we're tracking what we call the dimple, which is the center of the drop. And here on the left, we're using total internal reflection to track the nanometer resolution of the changes in the gap thickness between the drop and the film, okay? So we can calibrate this by looking at a lens with a known curvature. So, because our droplets, we don't know what the curvature should be, but a lens will have a known radius of curvature. And what you see is that for both techniques, on the top right is total internal reflection. You can see it goes up to about the wavelength of the light, which is 600 nanometers in this case. And we have very fine resolution, and that's what you can see in blue. And it tracks the actual lens curvature. And on the bottom right, you can see the interference microscopy can do the same, but it can track up to 10 microns, okay? And so combining these two techniques, we can get the full spatiotemporal profiles of the drop. This is the air gap underneath the drop that we're imaging, okay, for all time during impact, okay? So going back to this question of does this droplet ever make contact? If you look at the bottom view and the side view, and these are simultaneous videos, on the right, it looks like the droplet made contact, right? And so, but what you can see is, when we track the minimum air film thickness as a function of time, it reaches maybe about 100-something nanometers before it actually bounces off again, okay? So to try to give you a perspective, 100 nanometer is 1,000 times thinner than the thickness of your hair. That's how thin this air film is, and it prevents contact, right? You get so close, you get this close, but you never make it, right? It's kind of like the teacher who doesn't want to bump up your grade even though you're 90 or 89.99 something, right? So I'm sorry if I hit a sore spot there. Okay. So in graduate school, you will always be tasked with, if you end up pursuing graduate school or research, you're always tasked with, well, what did people do, right? And so what's already known? And so what we did was, okay, well, let me look at all the literature that looks at drop impact on, let's say, everything from a bath to the solid surface, okay? And so if you non-dimensionalize the film thickness, I'm calling delta, by the drop size or the radius, r, when that thickness to the drop size ratio is very large, that's a pool. So a lot of people have done that. And if the thickness of the film is about the thickness of the drop, that's also been done. And then drop impact on solid surfaces have been done for a very long time. But what was kind of missing in the literature was, well, what happens when you have a film, but it's much smaller than the thickness of the drop itself? And so that was something that was physically missing in the literature, okay? And so people who like to think this way, like what's really missing, what's an important question that hasn't been addressed in your respective fields, is something that students have a lot of fun time doing in the lab, okay? So I'm just giving a preview. So I'm a fluid physicist in that sense. And we were interested in what the physics that governs drop impact on thin films when we can remove things like the roughness-induced failure of the drop air film and try to understand some of the viscous effects in the thin film. Okay, so let me just give you the results. What we found was that if the drop impact inertia was sufficiently small, droplets also possess what's called surface tension. So this idea of free energy at the surface being very large, and surface tension doesn't like interfaces to be deformed. And so at low enough inertia, the droplet actually just totally bounces. But at an intermediate drop inertia, what happens is if you look in the middle, the air film will fail right at the center. And then if we further increase the inertia, the air film will fail instantaneously. Okay? And so there's a few length scales that are important to this problem. That is the center line thickness, which is we call the dimple, or HD. And the first kink away from the center we call HK. And there's a few dimensionless numbers that are relevant here if you see it. This one is called the Weber number, and this one's called the capillary number. The Weber number compares the relative importance of how much inertia you have versus how much surface energy is resisting that inertia. And the capillary number is comparing the viscous to the surface tension effects. Okay? Okay, so what we can do with our optics is track, again, the spatiotemporal dynamics. And so the air film underneath the drop is getting deformed, it's getting squished as it tries to impact the surface. And eventually the dimple collapses for this intermediate Weber number regime of about 6. Fluid magneticians love dimensionless numbers because we don't have to deal with units, for instance. Right? Dimensionless numbers are great. So, and then on the left, if we increase the drop inertia, the dimple doesn't fail. And so we thought that was interesting. How do we summarize those results? So what we did was, okay, so I said if your inertia is small, then you end up letting surface tension dominate. And so, and that also was already done before. If you track the thickness of the dimple, the center of the drop, then it surprisingly goes up. So here is a velocity. So if I'm increasing velocity here, and the vertical axis is the thickness of the center line, okay? Or the dimple. And it surprisingly goes up with increasing velocity, and it eventually goes down. And so this was unsurprising. The droplet impact dynamics on these thin oil films follow the same trend as on a solid surface, as long as the inertia is small. If the inertia is in an intermediate regime, what we found was, okay, well, if we get rid of the asperities, so to speak, typically in the literature they use the center line distance, the dimple thickness, as the characteristic length. But when you have materials like glass where there's random contact, and then you switch to an oil film or just a smooth surface, you start having controlled contact, and it's no longer random. And so the center thickness is no longer a relevant parameter. And so what we found was that the air film always fails at the center for an intermediate Weber number regime, where we could divide the contact time, Tc, by what we call a inertia capillary time scale. And that ratio is 1 when the air film fails, okay? And what was surprising, so let me try to skip to the main thing. What was surprising for us is that the faster you throw the baseball, you think the faster it hits the wall. But in this case, the faster you throw the droplet, it doesn't contact faster. It contacts at the same time between a certain regime, which was really surprising. And so, and then beyond this critical Weber number of up to about 10, what we found was that the droplet makes contact instantaneously. And we know that that is probably due to what we call disjoining pressure, which is caused by intermolecular forces. How many of you guys have heard of intermolecular forces, maybe in chemistry? Awesome. So this is intermolecular forces hard at work, making contact. And so all of these observations were summarized in a journal paper in Soft Matter some years ago now. For the sake of time, I'm going to skip my second presentation and go to my third, if that's okay. I would like to, how much time do I have left again?
You got about 20 minutes?
Oh, I do? Oh, okay.
Or
Awesome.
15 minutes, maybe 15 minutes.
Thank you.
I have some time for questions.
Yeah. Awesome. All right, let me skip to the polymers, because I said in the beginning that if you add a little bit of polymers, you can completely help droplets to stick. So if we can make the droplets to stick, then we don't have to use as much pesticides, then we don't have to worry as much, right? That one of the, anybody remember the 3 R's of sustainability? 3 R's from sustainability. Reduce, reuse, recycle. And are they of the same kind of level of importance, or is one kind of more weighted than the other?
I'd say reduce is probably the most important.
Right, yeah, we probably want to reduce, and so that's kind of the motivation behind some of the work that we're doing, okay? But, so we know from the literature and from different companies who are trying to formulate these solutions, polyethylene oxide is a chemical that they use in some of these additives in the sprays in dilute concentrations, but it hasn't been working out very well as intended so far. And I'd like to show a couple of videos that show, perhaps is pointing to why that might be happening. And the idea is that, okay, on your left, this is 1 parts per million. This is an exceedingly small concentration of polymers. You can see I'm sorry, it's a little bit busy, but if you just focus on this video for a second, the droplet makes contact right away. And from the bottom view, you can see how it makes contact. It makes contact using that dimple failure, like I just tried to explain, which is okay if it doesn't make sense. But on the right-hand side, you can see at a slightly larger concentration, and even higher Weber number, meaning there's even more inertia in the droplet. We did this on purpose. So there's actually 2 variables changing at once, but in theory, higher the drop velocity, the faster it should make contact, right? And so what was really weird was even at a much higher Weber number for a millimetric droplet size, with about very small amount of polymers, the droplet was bouncing right away. This should be surprising for you if some of you are paying attention, because I said if you add polymers, it should stick, not bounce. So what's weird is that there's something going on inside the droplet that is actually preventing contact, not enhancing it. And so I think it might be frozen again, but that's my fault, because I always try to downgrade the video files so that they're not so big. That's always like a tip, so that your presentations are not hundreds of megabytes. Right. And the image sizes as well. The image sizes sometimes can be so large that it crashes. Okay. But basically what I was going to show you next is a little bit more background on sort of the non-Newtonian dynamics. So in fluids, you'll learn about Newtonian and non-Newtonian dynamics. Oh, oops. And the idea is that Newtonian is the idea that if you apply a shear, you're going to get a linear response to the shear rate. But with the non-Newtonian drops, a lot of funny things can happen. And so non-Newtonian droplets you can think of, or non-Newtonian liquids, you can think of ketchup, for instance, is a classic one. You have to apply a certain shear before it starts flowing. And there are some other properties, too, that makes these liquids special. If you only look at the center of the drop, which is kind of cut off, there in the bright white spot will turn dark over time. And so what's happening is that when you have dilute amount of polymers, something is happening at the center of the drop that prevents the top surface from collapsing at the center, okay? And so that's kind of what I'm trying to talk to you about next, if this doesn't want to freeze. Okay, so the confusion around the literature was that, okay, 20 years ago we thought if you add polymers, it sticks. And then about 13 years later, there was another research group that showed under what's called Leidenfrost conditions. Leidenfrost just means if you're, actually some of you may have experienced it, maybe painfully. If you have a very hot surface and you pour water over it, the water never actually makes contact, right? You're already at film boiling, and so the droplets will break up, and it could even splash and hurt, right? But, and so under Leidenfrost conditions, where the hot surface is vaporizing the droplet very fast, the droplets will never make contact. But what's interesting is that on one hand, one group says that if you add polymers, the droplets will stick due to what are called extensional effects, which is a hallmark characteristic of these non-Newtonian liquids. On the left, this group said that actually if you add polymers under Leidenfrost conditions, the polymer drops will actually bounce even more, and they think that extensional effects are not important at all. And so what makes a good research project, in my opinion, is that if there's people that can't agree on a certain phenomenon, I think that's a fun place to study, right? And so that's kind of where we ask the question, okay, then what exactly is the role of this extensional rheology? And the idea of extensional rheology is that if you have a droplet and you have these little polymer chains which are big with respect to water molecules, they're quite huge, and they're so big that they're in these coils, and if you stress them, they can stretch out. Okay, and so there's only so much they can stretch, these polymer chains, and eventually, if you stretch them enough, they'll provide resistance. So it's not like the difference between water and honey, where there's resistance to shear, right? And you know that from experience if you try to mix honey. But not only is there that idea of viscosity or resistance to flow on a molecular scale, there could also be resistance to stretching, okay, whether uniaxially or biaxially, okay? And so, and that's called extensional viscosity. And so we were really curious what affects that parameter, okay? And how is the dilute droplets related to that effect, okay? Non-Newtonian drop impact is, non-Newtonian fluids are commonly neglected, even in mechanical engineering, but I think it shouldn't be, because there's quite a lot of applications for it, mainly in agriculture. COVID kind of woke us up to that, coding technologies, and even forensics, okay? Blood can be Newtonian or non-Newtonian, depending on who you talk to. One of the ways or some of the ways in which we can analyze the non-Newtonian effects is to compare the shear. So this is just taking a plate on another plate and rotating it and seeing if I run it at a certain rate, what is the stress I get back. And this rheometer is so sensitive, they claim, you can measure the torque that, let's say, the torque generated by a feather on the tip of your finger. This is what they typically say to us. That torque is how sensitive these rheometers are. And so at a dilute concentration, the shear viscosity is almost perfectly flat with respect to how much we shear it, which means that it's a Newtonian fluid. So viscosity is not changing with how fast we shear it. Now, if it's non-Newtonian, it will change. It will go down or up or things like that, okay? So it's weird because when we shear it, it seems Newtonian. But then if we allow the droplet to pinch off, and so this would be under uniaxial stretching, what we find is that, and this is a semi-log plot, and so what we find is that the droplet will actually form a neck, and it will slow down the pinch off, mainly due to what we call extensional effects, okay? And so these droplets, they seem like they don't have much, but actually if you stretch them enough, then they will have what's called a relaxation time. And the way we try to assess relaxation time is to compare two time scales. One is the time scale of observation, and the other is the time scale of the relaxation. Okay, so mainly from the polymer chains, but it's not limited to the polymer chains, right? And so if you take the relaxation time over the observation time, then, well, even mountains can flow in the time scale of God, right? Do you guys know what I'm quoting right now? Deborah, Judges. Mountains, the reason why you might not be recognizing it is because I said mountains flowed. It typically, in the translations we read, it'll say mountains quaked or something like that. But, in fluid mechanics, the Deborah number was named after precisely that. Deborah's song in Judges, okay? But, so the Deborah number in God's eyes is very small for even mountains, okay? But in our case, the Deborah number could be significant because our observation time is of the order of milliseconds and the relaxation time is of the order of milliseconds, okay? So that should be important. And so the way we try to understand the dynamics, I'm just going to kind of skip this forward now, is the main thing that we thought was interesting was when the droplet is impacting, and you're watching this from the side view, the top surface eventually collapses. We can take a laser sheet, chop the droplet in half, and observe the top surface going down at sub-millisecond resolution, or time resolution, and spatial, and you can see the droplet initially, okay, position versus time, so the slope gives you the velocity. It initially goes at the impact velocity, but then it goes multiple times faster when the top surface comes crashing in. If we balance the change in the surface energy to the kinetic energy, we can get an approximation for the top surface collapse velocity, which should be of the order of a meter per second, which can generate strain rates up to 1,000 inverse seconds. Okay? So why is that relevant? That's relevant because, I'll show you later, that I said if you stretch this enough, the polymers will stretch and it will cause extensional effects to kick in. So let me skip this for a second and show you. Now I take the same laser sheet, instead of chopping it this way, I want to chop it in the radial plane. So instead of axial, let's look at the radial. And what you see is that you can see the droplet with particles. This experiment, by the way, is not easy to do. Is really difficult to image just at the bottom of the drop and watch these particles stretch. We can track individual particles using particle tracking velocimetry and find that the strain rate inside the drop reaches several hundred inverse seconds and is large enough to kick in what we think is large enough to kick extensional viscous effects and therefore allows the droplets to bounce. And so, and this was all done by an undergraduate summer research student when I was at Princeton as a postdoc. She did thousands of experiments. And she's a graduate student now at Carnegie Mellon, doing better things. But the main conclusion is that when we add polymer additives, the droplets can bounce much better, all the way up to a certain threshold we call the disjoining or the intermolecular force limit. Okay? And so I think I should probably stop talking here and take questions. Thank you for your time.
Questions for our...
A couple minutes for questions. Do you have a question?
Yes?
So I'm studying welding engineering, so we deal with some liquid metals. So I know you're talking mostly about water, but do you know anything about how like drops of liquid metal that would react the same way, or
Yeah.
if that's a completely different deal?
Yeah, that's a great question. The question is, if you're welding and there's liquid metal droplets, can it entrain air? And the answer is yes. I know of at least 2 or 3 papers that talk about that, and I've never studied it myself. Why it is that liquid metal droplets can also entrain air, because that seems the density difference is just so astronomical. But that's a great question. that would be a fun project to start. Yeah.
All these results assume that we're doing things in normal air that's a mixture of nitrogen and some oxygen. How much would these results change if it were in something with a very different type of gas, like
Yeah,
hydrogen?
that's a great question. Yeah, how would our results change if we left the normal temperature and pressure region or regime NTP? We always assume in our classes, or not always, in some classes, I always assume that, almost, or not always, but most of the times. But yeah, that's an excellent question. What if you used heavier gases or lighter gases? So far, we've only tried this under very humid conditions versus very dry conditions. Since water vapor is lighter than air, we found no difference so far, but we definitely could try other gases. But what we found is there's a strong effect if the droplet itself is volatile, like if it's acetone, for instance, the dynamics are very different. But other than that, where the vapor pressure is very high, we haven't been able to generate a strong enough difference to be able to observe it. But we could try other gaseous environments for sure. Good question.
Any one more question? If you have more questions, our speaker will be here for a few minutes. Oh, there was a question over there?
Yes, please.
Sorry.
So, would there be an industrial or commercial application of this research to reduce the runoff of pesticides or herbicides?
Yeah, the question is there a direct industrial application? I want to say no, there's no direct connection. It's very indirect, mainly because we're physicists, less engineers, and so it's not direct, but I'd be happy to talk to, I have colleagues who do have that direct connection, and so I have I hear about the things that they're doing on a second hand, but that's a good question.
Just want to remind everybody, we'll be having lunch in the Joyce Room. If you want to join us and ask more questions, feel free to do so.